Hello and welcome to ELE 380, which is offered as an online course. In this course, we will discuss the fundamentals of control systems and learn about how to model dynamic systems, how to analyze the stability and the characteristics of the response of a system, as well as how to design controllers. Please take some time to review the syllabus, which is available on Blackboard, and also find the email that I have sent you. There is some useful information in that email, and I have asked you to respond to that email if you have received and read the email. So don't forget to do that. In this video, we're going to cover chapters 1 and 2. In chapter 1, we'll go over a very brief introduction on control systems. And then later in chapter 2, we'll talk a little bit about how to model dynamic systems. Control is a series of actions directed for making a system variable adhere to a reference value. So basically, we would like to do a control on a system or a process or a plant in order to control one or more specific variables of that system. For example, we might want to control the temperature in a room. We can only do that if there is a system like an air conditioning system that allows us to control the temperature. So the temperature is going to be the variable that we want to control in that system, and we're going to do the control by properly using the air conditioning system. The decision on when to start or stop the air conditioning would basically be the control job here. The reference value, when performing control, is the desired output variable. You're going to see this reference value or reference input a lot of times during this course. By reference input, we mean the desired value of the output. That is basically the desired value of the variable that we want to control. So in our example, if we want to control the temperature in the room, we have a desired value for that temperature. Say we want to keep the temperature at 74 degrees Fahrenheit, and that would be our desired value of the output, or also referred to as the reference input. Process, as I mentioned it earlier, is basically the system that we want to control. Sometimes this is called process, sometimes it is called plant, sometimes the system. They all mean the same thing. Fundamental structures of controls are classified based on the information used along the control process. There are basically two types of control. First one, which is the simpler one, is called open loop control, and another name for that is feed-forward control. In this type of control, there is no measurement whatsoever, and therefore the control job has to be performed based on a guess. For example, if in our temperature control, if we just decide to run the AC for a specific amount of time and we don't have any control on that during or after that amount of time, that will be called an open loop control. The temperature might reach the desired value that we have, or it might not. In the other type of control, which is more sophisticated and more useful, is called the closed loop control, also called feedback control. The reason we call it a feedback control is because in that case we are going to feed some information back to our controller. That information is nothing but the measurement of the output. So the output variable that we want to control is going to be measured, and then this information will be continuously used in the controller to make the decision. Here's our first a block diagram which shows a process as a black box. There are some inputs to this process and some outputs. Again, we might sometimes call this a system or a plant. They all mean the same thing. The first thing that I want to point out here is the input U. This letter U is normally used in this course as the input to a process, and that is what feeds the process or what activates the actuators of a physical system. We'll get to that later. The process provides an output, or basically two outputs here in this slide. You see the performance output and the measurements, which are the variables that we are measuring. Performance is normally not really considered an output, but it's more like a formula that we can use based on our measurements to find out whether the system is working good or bad. The more important output here is Y, which is the variable that we would like to control. And if we want to use a feedback control, which is the basic topic of this course, we are going to measure those variables, the Y variables. That's why you see measurement here. You can also see that there are some other inputs going into the process. The one is disturbance, or D. The other one is reference, or R. And the third one is eta, or measurement noise. These are sometimes not considered, especially in the beginning when we want to start learning about the control systems. These are the unwanted inputs. The inputs that will, the inputs or the phenomena or whatever that affects the process, but we don't want them. However, we cannot do anything to remove them. Disturbance is something that changes the way the system behaves. For example, wind for an airplane is a disturbance. It affects the performance, it affects the variables of the airplane, and there is no way to eliminate that. We don't want it, but we cannot eliminate it. Later on, we are going to be looking at disturbance a little bit and try to see what are the ways to design a controller in order to be able to deal with those disturbances. In other words, provide an acceptable performance even in the presence of disturbance. Reference, R, is nothing but the reference input we talked about in the previous slide, that is the desired output. The measurement noise is something that would affect the system if we have sensors. So in the open loop control, there is basically no measurement noise. But if we do any type of feedback, we need to have sensors and measure some variables. Sensors will introduce noise into the signals. Again, that most of the time exists when we have any type of measurement. We cannot do anything about that, but we can try to reduce the effect of that on the performance of the system by more advanced control strategies. In this slide, we'll talk more about open loop versus feedback control. So as I said earlier, in open loop control, there is no measurement, there is no feedback of information. The first block diagram shows an open loop control. You see that there is a reference value which works as an input for us. The output value is the output variable, the variable that we want to control. And you see that there is no closed loop, or there is no feedback here. The controller decides how to run the system, gives that information to the actuator. Actuator applies that on the process, and the process provides an output. So the controller does not have any information about what the current value of the output variable is. As opposed to that, in the feedback control, the second block diagram, you see this feedback path. Pay attention to the direction of the arrows. So in the forward path, it's almost exactly the same as the open loop control. However, there is a feedback path. The output variable is measured through a sensor, by a sensor. That information goes back to the beginning, and that will be compared with the reference value. This is very important. The reference value is the desired value of the output. What sensor gives us is the actual value of the output at current time. The difference between the reference value and the actual output value would be the error. The error is ideally should be equal to 0. So that is a very good information to be given to the controller. That way, when the controller sees that there is a very small error or 0 error, it knows that there is nothing much to do. But if there is a big error, there is a big difference between the desired output and the actual output, then the controller knows that it has to do something to compensate for this error or make the output get closer to the desired value. The rest of it would be similar to the open loop control. So the controller makes the decision based on the error, tells the actuator what to do. Actuator will apply that on the process. By the way, the actuator in our temperature and AC system example would basically be the AC system itself. So the system or the process includes the air conditioning and the room itself. The variable that we want to control is the temperature in the room. The actuator is the AC system. So the controller tells the AC to turn on or turn off or how long to work, and the AC system applies that to the process, so changes the temperature in the room. Let's see some examples for open loop and feedback control. In the open loop control devices that are basically using an open loop type of control, like an electric toaster or a standard gas stove or a traditional dryer, for example. These are the type of devices or systems that are using open loop control. For example, in a traditional toaster, you just decide how long you want the toaster to work, select that setting, and then start the toaster, right? So there is no measurement being done in the middle. If at the end you might get a toast that is good enough, or it might be even burnt. So it depends on how accurate your selection of the setting is in the beginning. There is no measurements being done during the process. As opposed, well, the controller is constructed based on knowledge or experience. In our example, the toaster example, based on our knowledge for a specific type of bread, we might know that we need to run the toaster for, say, 1 minute. So that's what we're going to do. So it's based on some knowledge. No measurements are being taken. With the feedback control, on the other hand, there is some type of measurement, and the controller is continuously checking the actual value of the output, comparing it with the desired value, and makes a decision. For example, automated filling up system, automated temperature control, even in the other examples we talked about, for example, a dryer. The modern dryers nowadays do have sensors to measure the humidity, for example. So they can decide how long the dryer has to work to dry everything inside that. It's not like we give it a specific amount of time and it works and then it stops. That is most of the time not efficient enough. The output is fed back for control computation. We talked about that. At the bottom, you see a type of a very basic feedback control. There is no computers involved in there. There is no processors. There is not even an electric signal included in this example. So this is a purely mechanical type of control. You can see that there is a water tank. This water tank has a ball float, and if we want to keep the level of the water inside the tank at a particular value, basically the level of the water would be our variable to control. We can do that through this feedback over here. There is actually not, you don't see an actual measurement in the sensor here, but it gives you an idea of what we need by feedback. The information about the level of the water in this example is basically fed back to our actuator, which is the water valve. You can see the water valve over here, through that ball float and the cords. So when the ball float comes up, that is when the level of the water comes up, that cord on the right side goes up, and that means the stopper or the water valve goes down and stops the flow of the water. And in the other case, if the level of the water goes down, the ball goes down, pulls on the cord, and then the stopper goes up on the other side, and the water flow starts. So the tank starts to fill up again. As soon as the level reaches the specified value, that cord goes back and the stopper will come back down and stop the flow of the water. At the end, the level of the water would be almost always kept at the desired level. The advantages and disadvantages of open loop control. Generally, open loop control is simpler than closed loop control. It does not require a sensor to measure. This is a plus. It does not introduce stability on its own. These are the good things about open loop control. But it has lower performance, and it has very much a lot less flexibility compared to closed loop or feedback control. On the other hand, with the feedback control, it is more complex than open loop control. Obviously, the controller itself is more complex. We need a sensor to measure the variable that we want to control. It might have a steady state error. We'll talk about steady state error later. And there are some issues with the sensor itself. However, that might be worth it. It might be still worth it. The picture on the right just shows you a very simple example of how an inaccuracy in sensor would affect the result. In this example, the control is not even automatic. It's a person that is standing there looking at the level of the water and then deciding when to open or close the valve so that it can control the level of the water. The person is actually looking at the level of the water, not perpendicular to that, so that introduces an error. He might not see the level of the water exactly at what it is and make the wrong decision. So the control decision on the feedback control depends on the accuracy of the sensor. All these problems exist. However, there are a lot of plus signs. The process controlled by well-designed feedback control can respond to unforeseen events. We already talked about disturbance. We talked about noise. There are also other things like aging or wear. A system changes, the behavior of a system changes in time due to aging and wear. And these are, again, unforeseen events or unwanted events. A good feedback control can minimize the effect of all of those. Second, it eliminates the need for human to adjust the control variable. So it reduces human workload. Feedback control can be done automatically. And in open loop control, normally, if we want to get an acceptable result, there should be a human to supervise the process and make corrections along the way. Third one, it gives much better performance. With feedback control, we can have a lot better performance out of the system. We will be able to adjust the transient response as well as the steady state response. We will talk in more details about all of these. Lastly, ability to stabilize an inherently unstable system. Some systems are inherently unstable. Open loop control cannot make them stable. No way. But with feedback control, we can make those systems stable. These advantages are all true if we know how to design the control systems and we know how to do it right. So that is the purpose of this course. We're going to first learn the basics and then learn how to design the basic type of controllers to satisfy all of these. After that introduction, we will jump to Chapter 2 on dynamic models. For designing a good controller, we always need a model of the physical system that we want to control. That is why we have to go through the modeling in this chapter. We will not spend a lot of time here because modeling is not the basic purpose of this course. We're just going to learn what a model is, how we can get those differential equations, and how those will be converted into transfer functions, which are what we will be working with. So we will learn that in this chapter. In the future chapters, we will not do the modeling, but we will assume that we already have the model of the physical system that we want to work with. Basically, for that step, we're going to use the results of the work of other people. We are going to start with a very simple example. A car, you can see a car over here. We are assuming that there is a force U applied to that and pulls that to the right. That is the engine force. And the variables that we can consider here for the car is x, which is position or displacement, or v, and v, which is the velocity of the car. We can also model that by the diagram you see on the right. In that diagram, you see m, the mass m is representing the car. U is the force that is applied to the car and pulling that to the right. There is a friction force which is applied in the opposite direction. You know, friction is the friction constant times the velocity. So B times V is the friction force. The displacement of the mass is x and the velocity is v, and you know that v is equal to derivative of displacement, so we can write v as x dot. Here we're going to pick a variable as an input to the system, what affects the system, and an variable as the output. So basically, we are talking about independent variable and a dependent variable. U here would be an independent variable, applies on the car, is applied on the system, and it affects the dependent variable, which could be either the position or the velocity. Here we're going to pick the velocity as the output. So this velocity v is going to be our output. What we want to do is to find an equation that relates the input u, this is input, to the output v. We want to find that equation. So first, we're going to find that equation in the time domain. Then we will apply Laplace transform on that equation. And after that, we will get the output over the input, which gives us the transfer function. We'll go through that step by step. To get that equation to relate the input to the output, u to v, we're going to use principal laws of physics, in this case just Newton's law. You all remember F equals m times a. F is the net force applied to the mass. In this case, it would be the force U, which is to the right, and the friction force in the opposite direction. So the net force would be U minus B times V. So F is U minus B times V. That must be equal to m times a. You know that V is the derivative of position x, and a, acceleration, is the derivative of v. So we can rewrite that equation in two different forms that you can see in the second line or the third line. We're going to go with the one in the third line, this one, because that is the one that has our variables and the input variable u and the output variable v. Remember, we picked the output variable to be v. Here's a point. We are free to pick any variable that we want in the systems. So in this case, let's say it is already told to us that we have to pick v, or based on our understanding, maybe the velocity is more important to us, so we pick the velocity as the output instead of, say, displacement. But we could do it the other way. If we change the output that we want to consider, that will also change our equation. It will change the transfer function as well. Anyway, so in this case, here is our equation. You see it has u, v, and v dot in there. V dot is a derivative of v. So we are dealing with a differential equation. What we're going to do is to keep everything that has v on one side of the equation and everything that has u on the other side. So I can add b times v to both sides of this equation and rewrite that as u equals m times v dot plus b times v. Now if I divide both sides of this equation by m, I will arrive at this other equation at the end. V dot plus b over m times v equals u over m. Remember that b and m here are constants. M is the mass of the car, and b is the friction constant. So we're dealing with a differential equation. Solving a differential equation in the time domain is difficult. I'm sure you are familiar with Laplace transform, at least to some extent, from other courses. Instead of working in the time domain, we can apply the Laplace transform on that differential equation, convert it to S domain, and work in the S domain. At the end, if we have to, we will do an inverse Laplace transform to go back to the time domain after we solve the problem. But here, take a look at this. V dot, if we take the Laplace transform of V dot, that would be S times V. Laplace transform of derivative of a variable in the time domain is equivalent to S times Laplace transform of that variable. So V dot, Laplace transform of V dot is S times V. Second term, Laplace transform of b over m times v. b over m is the constant, so we leave that there. Laplace transform of v is v of s in the time domain, in the Laplace domain, sorry. On the other side of the equation, 1 over m is the constant, so I put the 1 over m there. Laplace transform of the signal u of t is going to be u of s. As you can see, I'm using capital letters for variables in the s domain. On the left-hand side, we have two terms with v. If we factor out that v, we will get this equation over here. So now you can see that I have one equation, which is an algebraic equation, is not a differential equation anymore. That is why we use the Laplace transform. And in this equation, I have v on one side, u on the other side, output on one side, input on the other side. So if I'm interested to find the transfer function, I need to only find the output over input in the S domain. That is what the transfer function is. Output is v, input is u in this example. So the transfer function is v of s over u of s. Based on this this equation over here, if I divide both sides by u and then divide both sides by s plus b over m, I'm going to get this last equation at the bottom. That is nothing but the transfer function, which is a function of s that relates the input of the system to the output of the system. So we call this the transfer function. That is it for this example. So for other type of systems, we're going to follow the same thing. You start by writing equations, differential equations, using principal rules of physics if we're dealing with a physical system, and then manipulate those equations until we get one equation with the output on one side and the input on the other side, and the rest of the things are constants. And from there, we apply Laplace transform on that, and then find the output over input in the Laplace domain, and that gives us a transfer function. The reason we need the transfer function is because most of the methods that we will discuss about in this course are based on transfer functions. So let me erase some of these over here to the right. Just want to point something out about MATLAB. MATLAB is a very important tool, a very powerful tool. It is short for Matrix Laboratory. You might have seen that in other courses. Even if you haven't seen that before, do not be scared of that. MATLAB is very powerful. There is a lot of commands in there. There's a lot of ways to use MATLAB, but do not be scared. You're going to start small. The commands that you will need to work with in this course are very simple. They're all listed at the end of the chapters. The only parts that you need to use MATLAB with are in the assignments or the final project. And for those, just look at the end of the chapters. You can find whatever command that you need. Each time you will probably need only one or two new commands. If you cannot exactly find out how to use those commands, or you have any problems, make sure to let me know and I can help you. The reason I said that is because for this example, we're going to give values to our constants m and b, and also pick a constant value for the input u. So let's say m is 1,000 kilograms, b is 50 newtons seconds per meter, and u is 500 newtons. Remember, u is not supposed to be always a constant, but here it's our input. We assume we want to know how the velocity would change if we apply a constant 500 Newton force to our car in that example. We can use MATLAB to find out how the response would look like. First of all, we're going to use our transfer function, the one that we found in the previous slide. You can see that in this box over here. This transfer function, it has a constant in the numerator and s plus a constant in the denominator. All we have to do is to set up the numerator array, create an array that has the coefficients of the numerator. There's only one coefficient in the numerator, so we create this array, call that NUM, you can call it whatever you want, and put the only coefficient that we have in the numerator. In this example, it's just 1. So we put 1 over m, m is 1,000, so 1 over 1,000 is our coefficient in the numerator. Then we create another array and put the coefficients of the denominator in there. So look at this second one. Call it den or whatever else you want. Put the coefficients of the denominator polynomial in there. Now remember that you have this polynomial s plus b over m. This is a polynomial of s. Look at the coefficient of s. That is 1 times s, right? So the first coefficient is 1, the second one is b over m. So in this for the denominator, we have 2 coefficients. So put 1 and then b over m. B is 50, m is 1000, so 50 over 1000 is the second one. So this is a two element. These are two elements in the denominator vector. Next, we can use the step function. This is one of the simplest functions that you will start to work with it. You know what the step function is, right? So the step function is a function that is 0 before times 0 and then jumps to a specific value, stays there. Unit step function jumps to the value of 1 at time 0 and stays there. Okay? Step command that you see here gives the response of the system, or gives you the plot of the output of the system if the input is unit step input. So if the input is this in the time domain. What is our input now? You see U, we say it's 500 newtons, but we are assuming that that input is not applied before time 0. So basically, our input is 0 before time 0 and then jumps to 500 newtons. So the input that we are considering in this example is 500 times the unit step function. So in order to find the step response, we have to multiply our transfer function by 500. That is why you see this 500 getting multiplied in the front here. If we wanted to find the response to a unit step input, we would not put that 500 there. Everything else in there inside that step command is just what we created as the numerator array and the denominator array. We used NUM as the name for the numerator array of coefficients and DN for the denominator. So for finding the response to a unit step input, just do step numerator array that you created before, comma, denominator array that you created before. Make sure you notice that everything is case sensitive in MATLAB. So if you used NUM lowercase, you have to write it as lowercase NUM here. If you use it uppercase, use uppercase letters, you have to put uppercase there as well. Otherwise, it will give you an error. So this command here gives you the output if the input is unit step function. Here we have the 500 times the unit step function, so that's why we multiply it by 500. Let me erase this and then see the results. This is what MATLAB gives you if you write that command for this example. So you can see there is a plot. On the x-axis you have time. Y-axis you have the amplitude of the output. Remember, the output was the velocity. Now you can clearly see that even though our input, the engine force, is jumping from 0 to 500 at time 0, due to the constraints and due to the dynamics of the system or differential equations, the transfer function that we found, you can relate it to all of these. Due to those, the output velocity cannot jump from 0 to its final value. So it is going to start at 0 and then slowly increase to its final value, which in this case, in response to the 500 Newton force, the final value is going to be 10. How this value starts from 0 and ends at its final value will depend on the dynamics of the system. It could go faster, it could go slower, it could have overshoot, ups and downs, it could have oscillations or not. There could be different final values for the velocity. These will all depend on the dynamics of the system, or in other words, depend on the transfer function. Here is a second example. Two-mass system, which is a simplified model of the suspension system of a car. You see two masses here. M1 is the mass of the wheel, M2 is the mass of the car itself. See two springs, one is the spring between the wheel and the car, and the other one is represents the tire itself, which acts like a kind of a spring. There is also that damper in between the wheel and the car, which is also part of the suspension system. Here, the problem is a little bit more complicated than the previous example. We need to write at least two equations here, but it's still the same thing. What we're going to do is to pick an input to the system and an output, and then find at the end find an equation that relates the input to the output. Now look at this right here. This R is basically the height of the surface of the road, and this would be the independent variable, the input variable to the system. We want to see how the system is going to react, how the displacements x and y, displacement of the vertical displacement of the wheel and the vertical displacement of the body of the car will change if there is a change in the road surface. So we're going to pick R as our input to the system, that is what affects the system, and then the output is Y. Y is more important than X. We want to know how much the car itself is going to go up and down. So start writing our equations. Again, using the Newton's law, but this time we just have to write two equations, one for mass M1, another one for mass M2. Basically, for mass M1, we have three forces applied to that, two springs connected, and the damper. So write the forces, make sure you give them correct signs. So be careful with the directions. The net force will be equal to M1 times the acceleration of M1. Displacement of M1 is x, so its acceleration is x double dot. For the second equation, for mass M2, there are only two forces applied to that. One is by the spring and one is by the damper. Again, those forces are pulling M2 down, so if our positive direction is upwards, those two will both have negative signs. Add them up, that will be equal to the total force. The net force on M2 has to be equal to M2 times the acceleration of M2. Displacement of M2 is y, so its acceleration is y double dot. Here we have two equations. In these two equations, we see y, our output, and we see r, the input. But there is also an extra variable involved, which is x. We don't want x in our equation. We just want one equation relating input u to input r to output y. So what we can do here is to rewrite our equation somehow and remove x from the equation. So let's first rearrange our equations. The second two set of equations that you see down here are the same thing as the first two, just rearranged. And then we take these, go to the next slide, and apply Laplace transform. Again, as I said, if the Laplace transform of x is x of s, then the Laplace transform of the derivative of x is s times x of s. You might have seen this in other courses. We will discuss more about the properties of Laplace transform in the beginning of next chapter anyway. But for now, let's just apply the Laplace transform on the two equations we had on the previous slide. For example, the first term in the first equation was x double dot. Apply the Laplace transform on that. So for one derivative, we have s times x. For two derivatives, that would be s squared times x. So that is how we get the Laplace transform of the first term. Second term was b over m1 times x dot minus y dot. b over m1 is the constant, it remains there. Then instead of x dot, the Laplace transform of x dot is s times x. Laplace transform of y dot is s times y. So we factor out s and write that second term in the s domain like this. Similarly, we apply the Laplace transform on everything else on the first equation as well as the second equation. Now we have everything in the S domain. So here it will be easier to find x from one equation and replace it in the other equation. Whereas with the differential equation in the previous slide, we cannot really do that because it's not an algebraic equation. We cannot find x from one equation and replace it in the other one. So here, what we will do is we will find x from one equation, replace it in the other. We will get an equation that has only y and r as its variables. So that is where we will be able to find y over r. Remember, the output over input in the S domain or Laplace domain is nothing but our transfer function. So I'm going to skip how this is obtained, but it is a very good practice if you try to get from the previous slide, the previous two equations in the S domain, remove x from the two equations, and then find y over r. This would be a good practice for you. Try to see if you can get the exact same thing as the transfer function. Again, remember, transfer function is output over input in the S domain, not in the time domain. A third example would be an electrical circuit. This might be even simpler for you. Just one thing to mention here are the voltage current relationships for resistor, inductor, and capacitor in time domain, these first three equations, and in S domain. You can get the S domain equations by just applying the Laplace transform on the equations in the time domain. So what we can do here is we can actually skip getting the equations in the time domain and then applying the Laplace transform on that. It is easier for some examples, including this one, to first convert your circuit to S domain and write your equations in the S domain directly. So what you can do is convert capacitances to impedances. So for C1, the impedance is 1 over C1 times S. For this one, the impedance is 1 over C2 times S. Impedance of resistors are the same thing as resistances, R1 and R2. So now we would treat everything as resistors, or basically impedances. We can write two KCL equations. So we will get these two equations if we apply two KCL equations. The first one is applied here in this node. So V1 minus VI over R1 is the current that goes this direction. V1 minus VO divided by R2 is the current that goes this direction. And V1 divided by 1 over C1S is the current that goes this direction. That is the same thing as SC1 times V1. Sum of all those three currents has to be equal to 0. The second KCL, we can write it here. The current that goes this direction is VO minus V1 over R2, and the one that goes this direction is VO minus VI over 1 over C2S, which is the same thing as this. So we get our two equations. Why do we need two equations? Just look at the first one. On the first one, we have three variables, V1, VI, and VO. I forgot to say this. Assume that our input is VI and the output is VO. So we want to relate these two. Find an equation in the Laplace domain that relates VI to VO. That first equation that we get over here has VI, has VO, but also has an additional variable V1. We have to get rid of that. So we have to write another equation, like a second KCL, and then find a V1 from the second equation, substitute that into the first equation to eliminate that. So we go to the next slide. This one is another circuit, an RL circuit. Again, we can convert everything to S domain, like this one, the impedance of an inductor is L times S. L is 1, so the impedance here is 1 times S. The other three are resistors, so impedances are 1. We will write KCLs. Input is VI, output is the voltage VO. We want to find the one equation relating these two. So we will start by a KCL over here. V1 minus VI over 1 is the current going this direction. V1 over 1 is the current going this direction, and V1 minus VO over S is the current going this direction. Sum of these three has to be equal to 0. Also, we can write another equation. We need that second equation because you see in the first equation you have that additional variable V1. It's not only VI and VO. For the second equation, we can write another KCL, for example, or simply, even simpler than that, find this current based on the voltages, find this current based on the voltages, set them equal to each other. They have to be the same current because no branch is connected to the middle of between these two elements. The first one over here can be obtained as V1 minus VO over S, this right here. The second one can be obtained as VO minus 0 over 1. These two have to be equal. This will give you the same result as if you write a KCL over here at this node. Anyway, that gives you the second equation. Very easily, you can get V1 from the second equation as VO times S plus 1. Now we can replace that into our first equation and get this right here. The first row over here is the same thing as the first equation. It's just rewritten. Similar terms are combined. Now we replace V1 in there by its equivalent. And now we have an equation which has only VI and VO as its variables. All we have to do, keep all the terms that have VI on one side, all the terms that have VO on the other side. So with some simple manipulations, we can get this last equation, VO times 2S plus 3 equals VI. If we want to get the transfer function, all we need is the output VO over input VI in the S domain. So divide both sides of that equation by VI, then divide both sides by 2S plus 3. We will get this transfer function. VO over VI is 1 over 2S plus 3. We did a few simple examples. We now know how to write differential equations, whether there are mechanical systems or electrical systems or any other type of systems. We have to start with principal rules that will basically give us differential equations, apply Laplace transform on differential equations, go to the S domain, and then find an equation that relates your input to the output with no extra additional variables included in there. At the end, by finding the output variable over input variable, we will have our transfer function. This is very important. We need to be able to understand what the transfer function is because that's what we will be using to analyze control systems and design control systems throughout the rest of this course. You can do some practice and there will be some problems for you to work with in the first homework as well with modeling, but we will not spend a lot of time on modeling. As I said, in the future chapters, we will start with the model or the transfer function of a system, and we will not spend our time finding the transfer function in future chapters. That is it for chapters 1 and 2.